Thank you. Thank you for the introduction, and thanks for the opportunity to speak. Everything I will talk about is joint work with my graduate student, Soham Ghosh, who couldn't come here. I hope I do justice to some of the nice work he has done. So let me start by some background. It's certainly the story is long, and I'll just give you some context for the classical story. Let X be an abelian variety, complex abelian variety. If you're on the combinatorial side and you don't care about abelian varieties, don't give up on me. I'll become very combinatorial in 10 minutes or so. It has a dual abelian variety, which can be thought of as isomorphism classes of line bundles, which are algebraically equivalent to trivial line bundle, or they have first chain class 0. Anyway, some dual object is there. In general, this dual object is not isomorphic to the original one. And then the theory of Fourier-Mukai gives a nice duality theory at several levels between these two objects. So let me quickly draw some diagrams. So Fourier-Mukai, I'll stop writing Fourier-Mukai, but Fm is for Fourier-Mukai transform provides nice duality at different levels. And let me be more precise what I mean by that. So let me first you look at a very simple diagram, seemingly simple diagram. X times x hat has two projections to the first and second coordinates. Let's call this P1 and P2. And then this object has a very nice line bundle, which is responsible for a lot of beautiful theory for abelian varieties. It's called Poincare bundle. And I'll say in words what this bundle is supposed to be. So as I mentioned here, a point in the dual is in effect a line bundle on X. And X hat is the same as X. So a point in X is in effect a line bundle on X hat. And this Poincare bundle is kind of packaging this information as a single line bundle on the product. So if you look at the fiber over a point here, look at the Poincare bundle restricted to that fiber, you get a line bundle on X, and you might ask, what line bundle is that? Well, it's the same line bundle that the point that you put your hand on signifies, and vice versa. And maybe you should say at 0, it should be a trivial bundle to normalize things. So this is sort of packaging the duality of line bundles. And this story will come back in the tropical setting in a moment. So you get a few duality theories. First, you can look at the so-called derived category of bounded complexes of coherent OX modules, but just say some category that actually knows a lot about X, including all the sort of sheaf cohomology theory, a very rich object. You can actually give a map or functor between this category to this category, which is called, in this talk, Fx, Fourier functor. And this is, so what you do, so objects here are, say, some kind of sheaf or complexes of sheaves. What you do is you take that and you pull back along P1, then you twist it, you tensor it with P, and then you push forward. And all these words should have some appropriate adjectives in front of it, derive, push forward, and derive tensor, and things like that. So pull back, twist, push forward. Okay. And it turns out this is a equivalence of categories. This is already quite interesting because this is a very rich object. It knows a lot about X, and we just actually saw that it doesn't know everything. So two abelian varieties can, an abelian variety and its dual can be non-isomorphic, but these categories will be equivalent. So maybe Mukai, this is certainly an important observation that the right category does not know everything about the variety. But this is not, as I'll explain, this is not the level at which we will work, and I'll explain why. But there is a shadow of this at the level of Chow. So you saw Chow yesterday. In a combinatorial context, but there is, from this derived category, you can have so-called chain character maps. And for some reason, I have to tensor with Q, so I put a Q here. And you can ask what will be the corresponding F here if you bring everything downstairs. And you do exactly the same thing. If you have an algebraic cycle with, okay, rational coefficients, you can pull back, twist with the Chern character of P, which is exponential of P, twist with an appropriate thing coming from P, and then push forward. So it's the same idea again. And you get a map between the Chow groups. And this is going to be, so these are rings. But I'm going to say this is going to be isomorphism of groups. And you shouldn't be disappointed of abelian groups. So there are two ring structures here. There are two products, one of them coming from intersection, and the other one, X is a group. It's abelian variety. So that group structure gives yet another product, which is called Pontryagin product. And this map is actually more interesting. It takes intersection to Pontryagin product and Pontryagin product to intersection. So it switches things. So it's, yes, exactly. So product and convolutions switch, yes. So this is not disappointing. It's more interesting. This would be very interesting tropically. I'll get back to the tropical story in a moment. But then there is yet another level at the level of cohomology. So you have the cycle class map with Q coefficients. And you can again ask, what is this map now? These are now vector spaces. So what is cycle class map? If you have an algebraic cycle, you can triangulate it. We are working over C today. It can be triangulated, and then you can actually look at the cohomology class associated to that triangulation. And you get a map. And again, the map is what should be. If you have a cohomology class, you pull back, you twist using something coming from P. It's going to be the cycle of the exponential of P. And then you push forward. And at this level, it's kind of classically the least interesting one, but it's already more or less equivalent to Poincare duality. The fact that this is going to be isomorphism of vector spaces. This is very closely related to Poincare duality. So this is the least interesting, but already sort of is a pretty serious observation. Now, tropically is the subject of the work I'm going to advertise. The first line is, as far as I understand, hopeless. The derived category I mean, you will hear things about vector bundles in the tropical setting, and then you need to have a setup for complexes of vector bundles and all sorts of fancy things that experts tell me we are far from having a derived category. And to be honest, for me, this was not the motivation of being interested. I'm mostly interested in this line. And let me just say first line. My thought is this is hopeless. Second line is interesting. And it's work in progress, including with my students, but also I've talked with people in Frankfurt as well. And it would be, so maybe I should use the word moduli and matroid in my talk. So here goes moduli. So the Fourier-Mukai at the level of Chow is quite important. It's related to very important conjectures about Chow groups, Bailinson block, Bouville. For abelian varieties, there are open problems about various structures you can put on Chow groups, various filtrations. And they're quite out of reach. And one could hope that maybe if you understand the tropical story, you might have some way of degenerating the old conjectures to the boundary, at least provide evidence, or maybe you're lucky and you can even prove something about the generic fiber. But at least if you want to understand Chow group in the compactifications of moduli spaces, it seems like you need to understand what happens at the boundary. So it would be interesting, work in progress, and I'm not, I don't feel hopeless yet. For this, it's straightforward, and I will actually give a full answer to this. And as a consequence of the full answer, I'll also provide something called Poincaré formula for general tropical abelian varieties, which extends some of the earlier work. So third line is the subject of this talk. And it relates to some of the earlier works of people in tropical geometry, including myself. I had some work with Andreas a few years ago that sort of is nicely explained in this context as well. Okay, any questions about the classical story before I? Yes.
Something you could say practical keys rather than coherent keys?
So I don't do any of this is old school, and I can't say anything new. Anything you can find in Birkenhacker-Lang is all I know. I think the answer is yes, but I'm not an expert. I don't want to. Any other questions? Okay, so if you didn't, I hope I gave you a sort of feeling about what Fourier-Mukai is about. And now I'm going to be very concrete in the tropical setting. So, tropical Fourier-Mukai. So first of all, what is a tropical abelian variety? Really, most of the things even there was not about abelian varieties. It was about complex tori. So a complex torus is an abelian variety if some positivity holds. So let me not be too worried about the positivity condition. At some point I might, but so I'm going to talk about what is a analog of complex torus. It's going to be a real torus with some integral structure. So N is a lattice. By lattice, I mean something like Euclidean lattice. So you have, this is isomorphic to some z to the g and some bilinear form. On it. It's not the posted lattice. If you're very combinatorial, I'm not going that far. And R is the ambient vector space. real vector space. And then I'm going to fix another lattice. I'm going to call it another lattice in R. So the picture you should have in mind, you have this board vector space. You have this original lattice N, and you have this other lattice. Maybe I use dots. There are two lattices in this vector space. One of them plays the role of quotienting out the translation action, and the other one gives you the integral structure, the directions you're allowed to go. Okay? So X, the analog of abelian variety in this or complex torus is going to be the quotient in R by lambda. This is a real torus. I fixed the dimension G of dimension G with integral structure. This just means this other second lattice, well, N is the underlying lattice for NR. So if you like, just think about like R2 with Z2 inside it, and then fix another lattice to quotient out. Then the dual thing, I haven't yet talked about line bundles and Chern class and things like that, but very concretely, it turns out once you define all those things, the dual thing is going to be very concrete. It's going to be lambda dual. So this is tensoring with R modulo N dual. So you look at the dual vector space and quotient out, this is the right thing. So there is this so-called, maybe I have to say something about Appel-Humbert theorem. This is really classifying line bundles on the original, tropical line bundles on the original abelian variety. Maybe let me say what is a line bundle without actually defining. And I apologize, some of the definitions are rather technical. Please don't be discouraged. You have a full week. I'm happy to chat with you later on about the definitions, but some of the things actually I won't define, but I will use the word line bundle enough, so I have to say some feeling about what tropical line bundles are. So I'll give you actually 4 quick definitions, 4 names. You can think of it as a torsor over Fx, where this is the structure sheaf. So you should, any geometric space comes with a sheaf of functions. In this case, you want to think of piecewise affine functions with integer slopes, and integer means in the direction of n. Just like you can think of classical line bundles as OX torsors or OX star torsors, you might want to think about this definition. Another definition is more sort of topological. You can think of map of polyhedral spaces. Polyhedral spaces, which is locally trivial. Locally trivialized. Trivializable. This is very similar to what you learn in the manifolds class, maybe, but then the gluing function should be affine. You don't allow smooth functions. another way for abelian varieties, there is a classification or there is an understanding of line bundles in terms of group cohomology, which boils down to actually giving some Hermitian form, which has some integrality and some so-called semi-character. So some function theoretic explanation of what line bundles are like for complex numbers. And there's a version of that. So that theory is called Appel-Humbert theory. And you can find this in the book by Birkenhakel and Lang. In this case, you have some bilinear form on the vector space together with some linear function from lambda to R. So just like classically, line bundles can be classified with this sort of function theoretic data. With Andreas Gross, we wrote down the tropical Appel-Humbert theory in 2019, I think. So this was with Andreas. And there is a fourth definition, which is quite convenient, at least from combinatorial point of view, thinking of, again, as in the classical case, line bundles can be thought of as Cartier divisors. Well, Cartier divisors are a little bit more than line bundles. They're like line bundles and a rational section. So you can think of Cartier divisors. And Cartier divisors in this setting is some kind of a polyhedral thing. So a divisor is a balanced thing and corner locus, locally corner locus of some nice function. Yes. Correct, but when you have divisors, you have like theta divisor is going to be some kind of a polyhedral subset of this. So this is kind of it's like Rn is a trivial polyhedral space. And in fact, it's a tropical manifold. Here comes the word matroid. Rn is also some kind of a tropical linear space. It's a manifold. Hence, it has Poincare duality, which will also come in a moment. Okay, maybe if you're sufficiently fancy, you could think of all this information as being skeleton of Birkhoff space. One way of thinking about tropical geometry is via the lens of non-Archimedean geometry. But these are exactly what sit inside analytification of abelian varieties over non-Archimedean fields. Okay, so that's one technical definition. I didn't really define line bundles, but I hope I gave you the feeling that this is more or less what you know done tropically. Yes. Yes, they're all. Yes. So this was written down in a paper with Andreas. I think this is also, we definitely write about it, but this was certainly known in the same paper. I guess we write all these points of view in the same paper, but I don't think we maybe for Appel-Humbert, we take some credit, maybe. But the rest certainly were in the literature sporadically. So I also owe you the notion of, okay, let me maybe state one thing. So here's a fact. I could call it a proposition or a theorem, but it's really modulo this Appel-Humbert information. It's really a basic fact that there exists a unique. Okay, actually the uniqueness maybe it's a little bit more work. There exists a unique tropical Poincare bundle. Tropical Poincare bundle on X times X. So by this sentence, I mean there exists this sort of universal bundle on the product such that it has the property that if you restrict to fibers, you get the corresponding thing that you expect. And it's unique. The uniqueness classically is a consequence of seesaw theorem. And in this case, you can do something more explicit. And the way we construct it, so construction use this Appel-Humbert so as I was saying, Appel-Humbert is saying that to give a line bundle, you need to give a bilinear form and a function. And it turns out the function is actually zero function, and the bilinear form is the only obvious thing you can write down. So there is an obvious candidate, and then you check that that candidate works, and it has the properties that you expect from a Poincare bundle. And then you prove that it's unique up to isomorphism. I could call it proposition. We actually spent a few paragraphs checking things, but really, I mean, one knows this should work. So I'm almost ready to write the first theorem about, or the main theorem that we have proved about Fourier-Mukai transform, except I said it's at the level of cohomology, and I have to say what cohomology theory I'm going to use. So I'm going to have one more technical definition, and then hopefully it will be more explicit, yes. Can you repeat? Sorry.
How does one explicitly get a torsor or a partial divisor from Appel-Humbert data?
So Appel-Humbert data gives you, I mean, classically you're asking, or tropically? It's the same both classically and tropically. I mean, Appel-Humbert data essentially gives you this sort of check cohomology gluing information, and then you construct the line bundle from that gluing information.
How does it give you text data?
So can we talk about it after the, yes. But the question actually is perfectly valid classically too. You could ask, given a Hermitian form and a quasi-character, how can you actually write down a geometric line bundle? And actually, there's an appendix in Birkenhacker-Lang that actually works it out. Okay, so I want to write theorem A, but I still have to say tropical homology and cohomology. Just like line bundles, I'm not going to, well, maybe I write a definition, but not the full context. So, tropical cohomology theory. Maybe the significance of it, so this was introduced by Ittenberg, who will be here tomorrow, Katsarkov, Mikhalkin, and Zharkov, and has been worked out from different points of views by various people, including Andreas and I. It's a cohomology theory. It's a bigraded cohomology theory. Similar to Dolbeault cohomology. So you have P and Q. It's like Hodge numbers. Cohomology theory, which captures Hodge theoretic data in degenerations, capturing, at least that was the main point of the first paper in the subject, capturing say Hodge numbers, HPQs. In degenerations. You can find a precise statement in this IKMZ paper. There is a newer point of view using Lagerberg forms. This matches. This was I think, result of, was it Yell, Shah, Smaka? The Dolbeau theory. Dolbeau cohomology. Using forms. So that's sort of the need for such numbers. But let me give a definition, at least luckily for abelian varieties, these things are very explicit. In fact, you can write down what these cohomology groups are by using these two lattices that we have. But since I'm going to also need the first Chern class map, let me give another sort of fancy definition. So we have this. So this is a very quick technical definition, but you have this structure sheaf. We can look at the quotient map by the constant sheaf R. For some reason, we call this omega 1, lower one, or upper one? Upper one, right? Then there's upper one, or? Let's say H1, so sheaf cohomology of this omega 1 is what we would like to call it H11. And in general, you can have a P. You should be careful what P means. And then you can have HQ of omega P. That's a definition for these tropical cohomology theories. But the reason I wanted to write this definition is that this map also induces a map on cohomology, which I will refer to in a moment. And using this sort of, you can identify this with the isomorphism classes of line bundles, the same way that you can identify Picard group of nice varieties with H1 of X and OX hat. This is the analog of that. And you might want to call this map the first Chern class map. Sorry, this is a rather technical definition, but there exists this Chern class map coming from this information. The 1-1 cohomology, I've written it. This is not very useful definition. I don't expect, if you haven't seen these things, you're absorbing it. But let me say actually some very concrete, give me 1 second. Let me just say very concretely, this is actually not that bad in the case that, so everything I wrote was for any boundaryless polyhedral space, for example, but H11 of X, when X is what I was working with, and R mod lambda is just so I want, it's lambda tensor n dualize each one. So dual lattices, so it's very concrete. It's the dual lattice of lambda tensor dual lattice of n. And in general, HPQ, you'll have P copies of this and Q copies of this. So what's that? Exterior product, yes. So PQ of X is P of lambda stars Q of n stars. I hope I'm putting the P and Q correctly. I didn't take notes. Is that correct, P and Q, Andreas? Opposite? Right. So for the case of abelian varieties, this is very concrete. And for example, here, so you can think of this as essentially, if you fix basis for lambda and n, this is really just a bilinear form on NR with some integrality condition. So this can be identified with, for example, harm of lambda n dual and fix if you, so these are really bilinear forms on NR, which are integral when you pair lambda and n. Integral on lambda. And this is similar, okay, things like this have similar counterparts in complex settings. You might have heard Riemann forms and things like that. It's very similar situation. Sorry, Dan, you had a question earlier.
Maybe a previous question. Can you repeat?
Philip Yell, Kirsten Shaw, and Smaka. And the reason I didn't write was because I didn't know how to, is it CKA? I think he has left mathematics. That's the only paper of his that I have seen. Shaw, of course, is well known, and Yell also is not far from here, but his papers are still being discussed in this conference.
So there were ages when one referred to before Chambert-Loire, which was never finished. Is this finally solidifying that?
So so Chambert-Loire and Ducrot, the book, you mean the forms and currents on Berkeley spaces? Yeah. Correct, but the setup really relies on this thesis of Lagerberg in Sweden, which was over Rn, and then you can actually do it tropically. The setup, which is not complete, is sort of how to pull it back to Berkeley spaces and all that. But these things are very complete and published, and it's not conjectural. And the two, I mean, everything I say have various sources, but this isomorphism also is worked out concretely in this paper.
Identifying H1 affine with 6, you seem to embed and you're thinking of F after exponentially.
Yes, unfortunately, there's no exponential sequence in tropical geometry, and it would be nice, but this is like OX star, and this is like the map going to the connecting homomorphism. But this part of the map can be written down explicitly, but we don't have the exponential sequence. But you're absolutely correct that this is supposed to be the connecting homomorphism of an exponential sequence, which doesn't exist. Okay, so sorry, this was sort of the most technical definition, and Andreas and I have a 60-page article trying to work out these kind of things and proving various Kunet formula and things like that for tropical homology, and it's a pain, but now it's done, and we can move on. I can write down theorem A. Would it be sacrilegious if I don't wash the board? Oh, this is not bad. Yeah, I actually use the water system in the US for calculus classes, but we don't have boards like this that gets cleaned so well. Okay, so theorem A essentially says everything in the third line of the diagram classically works perfectly fine. In fact, I'll give a more refined information. So the map on, so this is joint work with Soham. Every theorem that I write is joint work with Soham. The map on tropical cohomology. Given by, I hope I've defined everything now. So we have this bi-graded cohomology theory on X and on X hat. And I said in words classically, I'm going to do the same thing I've been advertising. I'm going to, if you give me a cohomology class, I'm going to pull back along the first projection map and then use the ring operation, which is cup product, and twist it with Poincare bundle. It turns out I have to do first Chern class of Poincare bundle, and then exponential of that. Of course, you might wonder, what does that mean? This is just a formal notation for the Taylor expansion of exponential. So you do just C1 of P, yes, ring operation K times divided by K factorial, K bigger than or equal to 0. And when K is sufficiently large, this is not actually infinite sum. It's a finite sum. But that's a formal notation for exponential. You pull back, you twist with the appropriate contribution from Poincare bundle, and then you push forward. I hope I did P1 and P2 correctly. I think that's correct. So push forward. So this is the candidate for Fourier-Mukai. If you want to just repeat what made sense in this diagram, except here I was just doing it for a singular cohomology with Q coefficients, but I could actually extend this to C coefficients and then ask under the Hodge decomposition what will happen, and I'm answering that. I'm saying that what happens to the graded pieces of the complexified version of this line. And the theorem that I'm writing has the analog. It's true also over complex numbers. And it's closely related to Poincare duality. So this is well defined. So this thing is well defined. And the restriction I'll again denote it by fx to HPQs. The image is going to be HG minus Q, comma G minus P. So this is a flip there of X hat is an isomorphism. And I said it, let me not write it down for the interest of time. The same theorem is actually true classically too. So this is yet another indication that these HPQs are good candidates for classical HPQs. They have Hodge theoretic manifestation. Okay, and again, this is closely related to Poincare duality. Which was one of the main results that Andreas and I proved in our sheaf theory paper. And there was a different proof by JSS paper using Lagerberg form. So somehow, in this context, I guess I'll write matroids. You have Poincare duality when you have a sufficiently smooth object. It should be manifold or something, some generalization of. And spaces that are locally matroidal, locally given by tropical linear spaces, satisfy Poincare duality. And so it's kind of lame. In my situation, it's clearly a manifold. So here's matroid for my talk. Yes. 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 The correct version of it will be in the paper, but yes, if you restrict, you land here, and in fact, you get an isomorphism. Yes. So I said what these things are. These are the P tensors of here is the, so HPQ is really concretely this. So yeah, this is G-dimensional lattice. This is G-dimensional lattice.
You see some interesting matroids at this point?
I have not thought about it, but the most uninteresting matroid is the fact that my abelian variety is manifold, because the local picture is just Rn. So I have no, but I think Bernd is asking perhaps a more interesting question, that now you have a map between.
There's no only trivial matrix.
Okay, let's not. I take usually Bernd's questions very seriously, so let me not dismiss the question. I'll think about it. Okay, so yes. Okay, so I fulfilled the title of the talk, but really the whole thing is, maybe I should say also, for the proof of this fact, it's really computational. I mean, everything I'm saying looks fancy, but at the end of the day, it's linear algebra. We fix bases for lambda and n. We write these things very concretely, and then we compute determinants, and we even use fancy determinantal formulas. I had no idea, Jacobi's determinantal identity and all sorts of things, and we get equalities that we want. It's very, very computational. Yes. Yes. So you get the same. So you have a Poincare product, and yes, they switch. But so the main reason I wanted such a theory to exist, in fact, so this part ought to be generalized to Chow groups to have some very, I think, more interesting applications. But the main reason I wanted at the level of cohomology was some numerical identity. So again, with Andreas, we had proved some statement about its so-called Poincare formula for theta divisors. And then I learned there is a more general version for all abelian varieties, and I wondered if one can do it for all tropical abelian varieties. And the next theorem I want to write is that, and I think I can do it actually much faster now. And I have to be able to. I had a good system with my boards. Am I following the? Yeah, I have to switch this now. No. What should I do? So the next theorem, I can just write it down. And my goal is, after I write this down, I say how this was, this generalizes some of the known work in the literature. So here's an application. And classically, this is also one of the most important applications of the Fourier-Mukai transform at the level of cohomology, due to Bouville. So this is a generalized Poincare formula. Yet another thing with the Poincare name on it, which has nothing to do with the previous instances. Theorem B. Again with Soham. Let L be a non-degenerate line bundle. We should ask what is non-degenerate. So the notion of line bundle being ample or non-degenerate is a very complicated question in tropical geometry. This was already mentioned in the context of Bergman fans yesterday. What is ampleness? For abelian varieties, we are lucky because we have this notion of, again, Appel-Humbert data. You have a bilinear form, and you can impose positivity or non-degeneracy on that bilinear form. So if this first Chern class of L is non-degenerate, you say the line bundle is non-degenerate. If it's positive definite, you say the line bundle is ample. And it's a very good notion that works. So this means non-degenerate means first Chern class of L is non-degenerate. And remember, this is just a bilinear form on the ambient vector space. So you know what I mean by non-degenerate. Let E be this thing. Actually, let's call this E. Then you can write so-called polarization map from X to X hat, which takes a point here to pullback of translation by X. This is translation. Tensor with L inverse. Note that this is line bundle. So whatever I do here, I'm going to get a line bundle on X. And it turns out this is a sort of algebra. This has a Chern class equal to 0, meaning it's in peak 0, which is in X hat. So you do actually get a map. And then you can also check that this is actually a homomorphism. If you have X plus Y, it goes to, there's a theorem of the square, if you know the classical story. Then we prove the following formula. K, let K be a number between 0 and G. And what we prove is the following statement that has all this sort of fancy functions, fancy definitions that I have had so far in one formula. It's an identity of, let me just write it. So you can look at first Chern class of L, and then you can intersect it K times, and then divide by K factorial. So first Chern class of L is, you can think of it as a bilinear form, but you can also think of it as an element of lambda dual tensor L dual, and then you're sort of wedge producting it with itself. You can do that, or you can look at first Chern class of, okay, then you can, sorry, let me Fourier-Mukai this. So this object is going to be, so this is a, so this is in H11. When you do it K times, you land in HKK. And then when you Fourier transform it, you land in HG minus K, G minus K. So this is in HG minus K, comma G minus K of X hat. You can get another object in the same thing, and the punchline is that they are the same. So you can look at the same thing, G minus K times, divided by G minus K factorial. Now you're in HG minus K of X, and then you can use the polarization map and push it forward. Now you're going to land in HG minus K of X hat. You land the same place. Are they the same? Well, they are almost the same. -1 to the G minus K divided by this determinant of the bilinear form E, which is the first Chern class. So some identity, interesting identity with factorials, but it turns out this is a fundamental identity extending earlier work, yes, which I will wrap up. Maybe let me keep this board, erase this one. So a few remarks, final remarks. First thing is that this determinant of E means something very important. So there's a paper by Kensumi on theta functions on tropical surfaces, abelian surfaces in dimension 2, but he really proved something more. So essentially, it's in Kensumi. We have to sort of clean up his explanation, but determinant of E is in fact some measure of complexity of the space of global sections of L. So Dustin Cartwright had the definition of what should be in higher dimension sort of H0 of a line bundle. And Kensumi shows that this is really just actually dimension of some convex set. So he actually more precisely shows that the space of theta functions form a convex set, and its dimension is what Dustin had previously defined as the correct notion for dimension of the space of global sections. So in a way, so this is some kind of a Riemann-Roch for ample line bundles. So if L ample, and again, ampleness is mysterious, not for us. You just take the positive definiteness of E as definition of ample. So you can actually explain the boundary using Legendre transform. So I think it's polyhedral. Yes, it's a polyhedral. Yes, and the boundary points using the Legendre transform can be described. It's pure dimensional. In the case of abelian varieties with ample, it's very surprising. In fact, for even graphs, I had been obsessed with Riemann-Roch, and there's no such thing. There are very good examples. But yeah, for abelian varieties, things are nice. I think this is a very nice result that wasn't, I don't think he doesn't write this statement in his paper, even though it's implicitly in the paper. So I think at least as a service, we will write this down in the ongoing paper, but this is a Kensumi result. So this is some kind of a, and I call it Riemann-Roch because by ampleness, all the higher cohomologies, which we don't know what it is, should be vanishing anyway. So this is really what Riemann-Roch should be. And then maybe using this, you can actually call this degree of the polarization. You can call this T. And then these two observations together give the so-called Poincaré formula. So this was the generalized Poincaré formula, but the Poincaré formula for tropical curves is much simpler. It says the class of the WD image of Abel-Jacobi map, which I won't define for the interest of time, is the same thing as the class of theta to the power of G minus D divided by G minus D factorial. This was again a result that was kind of the source of many collaborations I had with Andreas. We made all these complicated things to prove this simple statement. Now I'm saying that this theorem and the result of Kensumi actually can be stated, can be phrased in a way that gives this for free. Also, so this was my result with Andreas. Now it's a corollary, corollary 1. And corollary 2 is a conjecture by Felix and Zakharov. Help me how to write your name, Felix. Oh, okay, that is too much, but I'm even more basic. And they have a conjecture modulo some pure dimensionality statement that says a similar formula for the prim case should also be true. And our formula also modulo the pure dimensionality. There is a prim version of that. Which is also in this context. So in a way, this formula classically is due to Bouville. And we show that tropically this also is true and source of many other instances that people have discovered. Okay, that's all I have.